Hello everyone, my name is Aaron Kaplan and this is my Physics 2 Project 2 presentation on resistance of wires. Now, what do we know about wires? We know that wires are part of a circuit and our circuits refer to what is known as Ohm's law. So Ohm's law states that the voltage is equal to the current times the resistance, right? And when we are calculating the resistance of wires, wires themselves have a resistance that's calculated by the rho multiplied by the length over the area. And why this happens is because wires can be made out of different materials, and each material has its own conductivity, which is why we have rho. And then the area refers to the cross sectional area, and L is length. The larger the wire, the more current that can flow through. And however, wires get their resistance, and the reason why it works is because the longer the length, right, or the smaller the cross-sectional area, or the less conductive that a material may be, will all affect its resistance and how difficult it becomes for electricity to kind of move through the line, right? So if I draw you a picture here, and bear with me, but here's my maybe telephone pole with wires, power lines maybe, and we have a move here from one pole to the next. This in the middle is distance d, and then if we have a second set of wires, and then we have distance d again with the same voltage, or sorry, not the same voltage, but the same current, or I, multiplied by the resistance as it travels further, right? So the distance between these two is d, but between these two here is 2d. The distance is longer, and because the length increases, so does the resistance of the wire. And when resistance goes up, then the current, which stays the same, the voltage here has to drop. And this gives us a principle called voltage drop, right? So using all of these equations here and understanding how wires themselves work when transmitting electricity, we can now factor for what my project 2 problem is being, and if I can just pull it up here. All right. If a main grid power station transfers 380 kilovolts on high voltage power lines to a small town requiring 10 kilovolts. we want to know what is the maximum distance the town can be from the mainland, right? And now there are a few more factors that we need to understand in order to be able to calculate the distance that this small town can be from that grid in order to achieve its 10 kilovolts needed. So understanding a little more, and I will give you some background about the high voltage power lines. Nowadays, they are what's known as ACSR, which stands for aluminum conductive steel reinforced. Right, so this is the material that's used in those power lines, which is important because by knowing the material, we get rho. So rho for this equation is going to be 2.8 times 10 to the negative 8th conductivity-wise. We also need to understand that high voltage power lines have a cross-sectional area of 2,500 millimeters squared. The length is unknown, and for this hypothetical problem, we're just going to use that I, or the current of the power lines, is equal to 2,000 amps. Okay, so first things first, understanding voltage drop and Ohm's law, we need to calculate the maximum amount of volts that can be lost throughout our circuit. So if we have a starting number of 380 kilovolts and the town requires 10 kilovolts, we are going to subtract the 10 kilovolts and we are left with 370 kilovolts, or 370,000 volts, right? And so now, if we have to account for 370 kilovolts is equal to that current of 2,000 amps multiplied by the resistance. And now we have to calculate for the resistance of the wire because it is technically unknown, not knowing the length of how far away this city is, but that we are trying to find out how far away this small city or town is. R then becomes 2.8 times, 2.8 times 10 to the power of negative 8 multiplied by the length over its cross-sectional area, which is 2,500 millimeters squared. And so if we want to convert this cross-sectional area to meters, it's equal to 0.0025 meters squared. And now we have to isolate for L in our equation. So if we have 370 kilovolts is equal to 2,000 multiplied by 2.8 times 10 to the negative 8th times L over 0.0025 meters squared. The first thing that we are going to want to do is get rid of this denominator right here. So we're going to multiply 370 kilovolts by 0.0025, 2,000 times 2.8 times 10 to the negative 8th times L, and we are left with, remembering that this is actually 370,000, we have 925 is equal to 2,000 times 2.8 times 10 to the power 8 multiplied by the length. And now we have to isolate this length yet again. And we end up with moving the 2 on each side. We now have 925 multiplied by L is equal to 2,000 times 2.8 times 10 to the negative 8th. And then if we want to go over here, now we have L is equal to 925 over 2,000 times 2.8 times 10 to the negative 8th. Right, and if we multiply these two on the bottom here, we have 2.8 times 10 to the power of negative 8 multiplied by 2,000, and we get 5.6 times 10 to the negative 5th over, under 925 is equal to L. If we solve for L yet again, we have 925 divided by that 5.6 to the power of negative 5. And this leaves us with a length of 16517.857, which is equal to 16,517,857. If we divide this now by this being meters and we want kilometers, we divide it by 1,000, and we are left with 16,517 kilometers is the maximum distance here, or maximum length, that L can be before we exceed our voltage drop of 370,000 kilovolts. And this is hypothetically and theoretically the longest distance that a small town that may be off-grid can be from the mainland if it is using high voltage power lines to supply the power to the town without going under that 10 kilovolts required to power the town, essentially using data from real life high voltage lines that are used in cities today. I hope you guys enjoyed my presentation. Thank you.